Hey everyone, and welcome back to the channel. Today we are diving into a very specific topic of PostgreSQL, the hash index. We'll see how it works under the hood and understand if it's better than B-tree index. So what is a hash index and when should you use one? Hash indexes are quite versatile and can work with many different data types, from numbers and text to JSONs. However, for the best performance and distribution, it's ideal if the values in your indexed column are mostly unique or highly varied. Let's start with understanding the analogy. Imagine you have a gigantic multi-volume encyclopedia. To find a specific topic, you typically go to the very back of the final volume. Find the alphabetical index, locate your topic, and it will tell you exact page number in a specific volume. Hash index works exactly the same way, but you don't even have to scan any alphabetical list at all. You immediately know where to go. So how does it actually work? At its core, a hash index works on a principle very similar to a hash map or hash table in programming languages like Java or Python. If you're familiar with the concept, you're already 80% there. If not, don't worry, we'll break it down. When you create a hash index on a column, let's say a name column, in a user's table, PostgreSQL doesn't store the names themselves in a sorted list. Instead, it does the following. First, it generates a hash. PostgreSQL takes the value from the column and applies a hash function to it. This function's job is to convert that value into a single fixed-sized number, which is called hash. This number is a unique fingerprint of the data. The most important rule of a hash function is that for the same input, it will always produce the exact same output. Next step is to find a bucket. PostgreSQL needs a place to store this hash. It uses a series of storage locations called buckets or pages. To figure out which bucket to put the hash in, it takes the hash value and performs a simple calculation, most commonly the modulo operation, which gives us a page number. And the last step is storing the pointer. Inside that specific bucket, PostgreSQL stores two pieces of information, the original hash value and a direct pointer or address to the exact row in the main table, where the rest of the data is stored. So how do we actually use this index? For example, to find a record with name Jane, the database performs the same steps we just outlined. A value is converted into a hash, that hash points to a bucket, and the bucket gives us the direct address of the row in the table. It's a remarkably straightforward process. The biggest advantage of this method is its incredible speed. The operations are all extremely fast and do not depend on the size of your table. Whether your table has 100 rows or 100 million, the time it takes to find a specific item is nearly the same. This is what we mean when we say the search performance is O1, constant time. Now that we understand how hash indexes work, let's quickly break down their main advantages and disadvantages. As I mentioned, hash index is really fast. It provides extremely quick data retrieval, especially for large datasets. It allows for constant access time. Regardless of the table size, the time to find a specific item remains almost the same. In some specific cases, it can consume less disk space compared to other index types if the index values are very long. Regarding the limitations, because a hash index relies on a simple one-way hash function, it can only be used for strict equality searches. It cannot handle operations like greater than, less than, or ranges, and is completely useless for sorting data. Also, it cannot be used for finding records based on partial string matches. So when can a hash index be more efficient than the default B-tree index? By the way, if you'd like more background on how B-trees work, you can check out my previous video. Hash indexes can be preferable in two main scenarios. First, for very large tables with equality lookups only. We're talking about hundreds of millions or even billions of rows. At this scale, a hash index may provide slightly faster lookups compared to a B-tree. Also, it might be useful for large or complex keys. If the index column contains long strings or large JSON fields, storing and sorting those values in a B-tree can be costly. A hash index, on the other hand, stores only a 4-byte hash value plus a pointer, while a B tree stores the entire key. This can make the hash index significantly smaller. However, for most common use cases, B trees still win. They offer much greater flexibility, supporting a wider range of query types, including sorting and range searches. Additionally, the performance difference between a hash index and a well-optimized B tree can often be minimal or even negligible in real-world applications, especially thanks to the PostgreSQL's excellent B tree optimizations. Ultimately, the choice comes down to your specific workload and trade-offs between speed and flexibility. That's it for today. I hope it was useful. Thanks for watching and see you in the next video. Bye!